Welcome back and hello again. Now let's talk again about dependability. We mentioned dependability and its components already in the previous video, but only in an intuitive way. Now we are going to see more details and a formal definition of what is dependability and what are the different components of dependability. Just a second. But first, let's use again the same example which I was using before. I said dependability has these 5 pillars or these 5 columns, and we use the example of a car. So let's use the same example again, just to repeat before we go in detail what is this. Okay, safety is the property of avoiding accidents. Let's say a safe car is a car which will never produce an accident. For example, a car which never works is safe, but it's not what we need. A car which is safe, okay, the brakes work properly, the driving wheel works properly, the steering and everything. So you can rely on this car, it will produce no accident, and if something fails, it stops before you have an accident or a collision. The availability is the probability the car will be ready to be used when you need it. For example, if the car needs a lot of maintenance, it is never ready, it has a very low availability. If the car can be used always, you don't need to go to the shop to repair every time, then it has a very high availability. The probability you can use it next Monday at 8 is very high. Reliability is maybe something similar. It begins when you begin using the car. We assume when you begin using the car, it works properly. And then you will need it for a period of time. And the reliability is the probability the car will be working in the right way for this period of time. For example, from home until your work. They are different. Let's assume a car with a high reliability but low availability. The car needs a lot of repairs. Okay, it's almost always in the shop. But when it is repaired, you start and you continue working until you arrive at your office, and it has a high reliability. But you cannot be sure will you be able to use it on Monday, or after using you have to bring it to the shop to repair, not to repair for maintenance until you need it again. And the opposite, a car with high availability, it's there, you can take it whenever you want, you never go to the shop, you never give maintenance, but then you start driving and then it fails. Then you have to pull back. You can start again, it will go, but it fails again. And you can start again and so. So it has a high availability, whenever you want you can take it, but the probability you will come to the work without braking, it's very low. Okay, and these are related to persons. These are related to physical events, and this is integrity and confidentiality is related to persons maybe with bad intentions. Integrity is if your data is safe. If no one from outside with malicious intentions can change your data. For example, let's take an account in a bank. High integrity is no one may change your data in the account of your bank, only authorized people or yourself. Confidentiality is something different, is if your data will be published without your consent. For example, it can be very confidential, your data will never come out, or if it is not confidential, there are data leaks and everyone can see your data at the bank or at the car. Okay, now let's see a little bit more formal definition of this parameter. For this, we are going for the quantification of dependability, how dependable is my system, how reliable or how available. We need to use statistics. We cannot be sure it will work for 3 hours for sure, but you can say the probability it will work for 3 hours. You cannot be sure on Monday you can take the car, you can say the probability you can take the car on Monday. So we are using statistics and probabilistic values And for this, we are going to use Gaussian distributions. I hope you remember the parameter of the Gaussian distributions. It had a mean value, the probability we expect, and we have a standard deviation. That is how certain is this value of this probability. For example, if a system behaves always the same, we can be very certain about these values, and this Gaussian bell will be very small. If the system does everything sometimes very different, sometimes it works for 10 days and sometimes only 10 seconds, then we have here a very wide standard deviation, and it will be something like this. Very wide standard deviations or certainty about these values are very low. So we don't know. We have a mean value. The mean value is maybe 1 hour, but sometimes it's only 1 second and sometimes it's 10 days. So that's a bad situation. Much better is if it is deterministic, always behaves almost the same. So low standard deviation. The mean value will be again 3 hours, but we are almost sure about 3 hours, maybe 10 minutes earlier or 10 minutes later, according to, to measurements. Do not forget, all this data is according only to measurements. Now let's see these parameters. We have a system, it starts working at time 0, and this period of time it works properly. And then we have a crash. We cannot avoid this. The system will stop working. And then we have a recovery time, and then we continue working again, and the system will continue working until this time. Okay, and we can say the crash will come. You cannot avoid this. We shall know approximately how long will it work before the crash comes. But remember, it's a mean and the standard deviation. How sure can we be about this data? And then, if it crashes, it's very important, be ready to restart. If you don't start again, you have this situation, you crash, and then end of execution, and that's a very bad situation. So this is the end of your system. We don't want this. We want to recover and continue working. In these cars, in the example of a car, it fails, bring the car to a shop, and 2 days later you can take it again. Or if you have self-recovery systems, maybe this time to recover is only a few milliseconds, and the systems will reconfigure and continue working again. This restarts. Okay, be ready to restart and restart the system. Okay, now let's see these parameters. We make some measurements, and remember, statistic values, and we take this. The definition of reliability of a system is a function of time. R is the probability, and this is how long. And defines the conditional probability that the system performs correctly through the interval time t0 to t, given that the system was performing correctly at the beginning, at t0. So this is the reliability, the probability. You take your device here, you want to use it until here, not because it fails, but because you need it until this point. And this is the reliability for this time period from t0 to t1. But we say at this point, it has to be working. So when you take it, it is working. And then the question is, will it continue working as long as you need it? Okay, if it is working at the time when you need, this is the availability. Okay, we define the availability of a system is a function of time, of a time point, which defines the probability that the system is operating correctly and available to perform its function at this stand of time t. So you take only this time point and say, what is the probability and this moment it is working? So for example, next Monday at 7 o'clock in the morning. Okay, are all systems online? So you can see the difference between availability and reliability. Good. And for this, we make some measurements. We start the system, and we have the time to failure. Just the time to failure. How long does it work from here to here? And then you recover. And this, you take the time, how long did you take to start working again? That is time to recover. And then it continues working again, maybe this time less, and then you recover faster, because you know already again, and this is again the time to recover, and you continue this. And then you can measure what is the time the time from between failures. So here you have a failure and you start working, and here you have the next failure. So you measure the total time between failures. And this is the time to recover plus the time which is working properly. And this is only one measurement. But what we need is statistic values. This is a concrete case. We need the statistic value. So we perform this measurement many times, thousands of times, millions of times if possible. And then we have this Gaussian bell, this Gaussian distribution, and then we can see what is the mean time of failures. Then we are talking about the mean time of failures, this, the mean time to recover after thousands of measurements, and the mean time between failures, which is the sum of mean time to failure plus mean time to recover from here to here. And of course, I said before, another important parameter is the standard deviation. If it is always almost the same, this is always about 3 hours and we have looked, then we can be very, very confident about this data. If sometimes it's 10 minutes and sometimes 10 days, then we have here a very big standard deviation, and we are absolutely not confident about this data. These measurements, we have a problem with this system. And now, with mechanical parts, it works very nice. With software, it's a problem to make these measurements because the behavior of software and the crash doesn't depend on how long it had been working, but on the new circumstances, the new data. Maybe you are repeating always the same data, always the same computations, and it can be working for years without crash. Or it begins working and you give new data which produces the crash, and it will crash in few seconds. So with software, it's a very difficult measurement, this mean time to failure. Mean time to recover, okay, this can be done, you know the time to recover. But the mean time to failure, you cannot make like this. You need to consider which data are you using, and maybe it will be better to consider not the mean time, the time to crash, but how much different data statistically you provide before it crashes. A total different topic. Okay, now let's take about safety. I said before, safety is to avoid accidents, even if the expected function is not provided. Okay, a car which doesn't move is safe, no accidents, no dangers, but no function. If it moves, it has a function of probability of an accident, of course. Okay, let's see. Let's assume an accident can occur only after a crash, let's say, of the embedded controller. Then we have the probability the system will be working properly. Then we have a crash, and then we have the probability. It doesn't mean after the crash we will have automatically an accident, but it depends how it crashes. It depends if it has a fail-safe or a degradation of functionality, or what occurs here. And then we have the probability of an accident after the failure of the system. Okay. And then we have the other things, integrity. If the system is down, is not working, then actually you don't have any problems of integrity. It's not working, no one can access your data. The integrity is a risk only in the time when the system is working. Hacker attacks, for example. And the other thing is the confidentiality. If you have data leaks, if it is possible to extract data of your system without your consent or without you want. And this is always in this time where the system is operable. If the system is down, then actually we don't expect data links. It will be something different if the system is down and you can take the data with you. It's still the data. But if you have access, for example, with internet or something like this, it is only in the time when the system is working properly. Okay, now a few words about confidentiality and security. I said before, privacy and security impairments are human-related. It can be accidental or with malicious attack. If it is accidental, for example, operator careless, he didn't take care, it was not a bad intention, but it released the data or changed unintentionally data in the system, control information, for example, or improper reaction to safety warnings. Malicious attacks are hackers, viruses, and the like. Okay, the privacy is compromised when confidential of personal data is disclosed to unauthorized parties, persons. And security is breached, for example, when account information in a bank is improperly modified, with or without intention. Okay, let's take an example, the opposite about the privacy and security, or safety and security. Let's go to this point. We were talking about these two components. This is security, this both together, and this is safety. And then let's take an example with a door, a simple door. And let's talk, it's safe or it's secure. What does the door provide, security or safety? What do you think? Or maybe could be the same. Let me show you. You want a safe or a secure door? What will you say? Is this door safe or is this door secure? For example, this safe, its name is safe, with two very heavy doors. I will say it has a higher security because it's very difficult to access what is inside. So only authorized people who knows the combination can access the data inside, or the money or whatever you had inside of this treasure, of this safe. But it's dangerous. For example, this door, which you have a lot of keys to open, maybe you will say it's secure, but it's very unsafe. If you have an accident, for example, a fire, and you need many keys in order to open this door to be able to run out and save your life, and you cannot because it's too much to do, then this door is not safe. It's a very dangerous door. So you can see it's the opposite. A door with many security is a dangerous door, it's not safety. And a door which you can open very easily to run out, it provides safety, but it provides no security. Everyone can go in and out. So it's the opposite. So the best thing for your safety will be no door. Let it open. If something occurs, you can go very easily out of the building and you are safe. But it is very insecure. It's not security. And a very secure door has a lot of locks, very difficult to open, provides security, but in case of accident you cannot go out, so it's unsafe. So you can see it's actually the opposite, safety and security. Okay, and now let's come back to statistic definitions of the value which we want. And let's begin with reliability. Do you remember reliability is the probability the system will work properly for the time you need it? When you start at home, drive it to your office. And this is a time. We have to express every time as function of time. Okay, and let's call R is the probability of reliability. Is from T, we say at time point T it was working. And now the question, will it continue working for a delta T for this extra time? And this is the probability it's working at this time, multiply by the probability it will continue working by this time. And this is 1 minus error rate. Do you remember error rate is expressed in failures per unit of time? Maybe 3 errors per millions of hours. And the multiplication of this both is this. The reliability for this time period of T is E to the power of error rate multiplied by the time period. Okay, it's a function like this. It drops very quickly and it comes closer and closer and closer to zero. So if you have an infinite time, this here will be infinity, then the probability it will be working for infinite time is zero. If you have a very short time, only 1 second, let's say this is 1 second, then the probability it will be working is very high. Of course, the shape of this function depends on this. And it shall not be as quickly as this, or this shall be maybe 1 year or something like this. But be aware, the time here you use and the time for your error of failures per unit of time shall be the same unit. For example, hours or millions of hours, of days, of years. But be aware, both here, this and this has to have the same unit. Okay. And now let's see the mean time to failure. The mean time to failure is expressed as the probability. This was one measurement. And we have to have many measurements. Let's say we have infinity measurements. And then we have the reliability of each of these, the integral of this multiplied by the time which we were observing the system. And if we take a look to this integral of this function, the integral of e to the power of x is e to the power of x, then the probability, the mean time to failure is 1 divided by the error rate. This is the error rate. How many errors do you expect per unit of time? An example which we saw before is, for example, 10 to the power of minus 9 errors per hour. This means you can run 10 to the power of 9, 1 billion hours before you get a failure. This is an example. Okay, and this is the mean time to failure. This will be, use a second. Oh, sorry. This will be this. 1 divided by the error rate. Well, it was expected. The only thing you have to do is to solve these differential equations and you will get this. Okay, and now this assumes the system was working, then there is a failure, and then it's down. This is the reliability. After the system is down, it doesn't count anymore. It doesn't count if you perform a recovery or not. The system has failed. And then this is the reliability of your system. You can restart the system and begin again, but this is another thing. Okay, the reliability is the probability that the system remains in the good state here in the interval from 0 to t. Here doesn't matter. Okay, and this is the reliability of this time is what we saw before. The reliability of this time plus multiplied by this function, and this gives this. The reliability for a period of t is e to the power of minus error rate multiplied by the 10 which you want to want. And this is a function like this, and this will be the mean time to failures. Okay. Okay, and this is what we saw. That is exactly the same as the inverse of the error rate. Okay, and now let's talk about availability. With availability, we assume after a failure, there is a repair. If there is no repair, if you failure and then the system is gone for always, then you have a availability of 0. You can use it only once, it fails, and from there to the end of time, it's dead. So availability of 0. But let's assume there is a recover and you come to the up situation again and you can try again. Okay, the availability, let's say the probability A as function of a time point. Is the fraction of time that the system is up and during the interval 0 to t. The ready to use availability is the limit from when we are going to infinity of this probability. So if you take an infinity time, then the probability at any time that the system will be running. Of course, nothing will run to infinity, so let's assume here years. Okay. The point-wise availability in this time is the probability that the system is available at this time t. Okay. And you take a look to this. This is the timeline of a system. Running, recover, running, recover. And you make arbitrary. You take this point, what is the probability you land here, then the system is up, you can use it, or the probability you land here, then the system is down, is not usable. So it's not available. So you can see this probability, this availability is a function of this mean time to failure and the mean time to recover. If you take the time from here to here, then the availability here will be the mean time to failures divided by the total time. So it's the same from the mean time to failure divided by, again, mean time to failure plus mean time to recover. If the mean time to recover is going to 0, if you can recover your system very fast and the mean time to failure is going very long, then this is approaching to 1, but will never reach the 1. And now, let's make this difference. When talking about reliability, we talk about the probability that in a given time the system will be working, and after the failure is the end. It is not interesting anymore. When talking about availability, we are assuming the system is going to fail, and then we have a repair, and then we are considering both of them, the time working and the time not working. Remember, okay, and this is what we saw before. And if the mean time to failure is going very big and the mean time to recover is going very low, then we are approaching 1. So it will have a very high availability. But now when we are talking about down, the system is down, not working. Down is not the same like down. For example, we have these cases. The system is working properly, and then we have a failure. We can go in a safe state, and then everything is okay. Or we can have another failure, and then we can go in an unsafe state. And from this unsafe state, we can have an accident. So this is the terrible situation. And we can have this other situation, which is very normal. The system is working properly. We have a failure. We have a short fell down. We repair, and we continue working. Or we have a failure. We go to unsafe down, then maybe we have an accident and there is no way back to working again. So even if we have implemented some recovery after the accident, there is no recovery anymore. That is the end of the history now. The other possibility is it goes down, safe down, and normally the only way is to go up, but by mishandling. This is a handmade. You can go from safe down to unsafe down, and maybe then to an accident. For example, if the system is not working properly, it is recommended to stop now, and you continue driving, then maybe you are going to have an accident. Okay, this was only a short talk about down and not down, but here there is something more. We are talking about this mean time to failure, and this is a function of this error rate. And we assume the error rate is the same, but actually the error rate is changing in the time which a system is running. So error rate is not a constant in the period of time. Maybe you know this bathtub curve. When the system is very new, the probability of failure is decreasing. So at the beginning, the system will be working very nice, properly, and then you will have many failures, and this is the burn-in time. And after these failures are eliminated, then the system will continue working with an almost constant error rate. This is the useful lifetime. And after a long time, the system has worn out, then you begin having more and more and more failures. For example, a car, at the beginning, when it's very new, you will have a lot of failures. Then with everything, all these burn-out errors are corrected, the car will work properly for a long time. And after maybe 10 years, you will have many failures and more failures and more failures until you take the decision to change the car. This car is not appropriate anymore. So we have to consider this error rate to be a constant only in this useful life. And this has to be considered differently. Let's take a look. This is time, for example, in years, and the probability that a system is still working. Let's say you produce 1,000 of these time units, and then you count how many units are still working after this time. And then you have this at the beginning, when all units are new, then a lot of them will die very early, what we call the infantile mortality. So in the first months, a lot of these units will stop working. And then you can use these units for this time of period with almost no failure, and then they begin more and more and more failures. This is the wear out until all units have died. And let's say after 100 years, we can assume all units are already died. And this is the path curve. This part is here. This is from here to here. And this here is from here to here. So the best thing to use the system is in this part. And then let's find this part. To avoid these problems in safety critical systems, these failures could be accidents, and we don't want accidents. So we shall find all these units which are going to fail and eliminate them before we are using in real systems. For this, there is a burn-in and stress testing. For example, we can have oven, and in oven we can have this burn-in with higher temperature, the aging, or with radiation. With a higher temperature and with radiation, we can make a fast aging of the unit. So let's say at the beginning, with no burnt parts, we take all parts which are produced and we use them as they are, then we will have this mortality of the system. At the beginning, a lot of them are going to die, and then we can keep using a few. They are going to continue dying, and then until here, and then it will go faster. That is time in years, for example, from 1 to 12 years. But if we select out this, okay, we make the burn out of this, and all these units which fail at the beginning are not going to be distributed, are not going to be real use in the system, then we have a curve like this. All units, the units which survive the first month, are very likely to survive for a long time. So we move this part to here if we eliminate these units. This is what we do in this burn-in test, or trying using the system before we deliver or begin with a real application. Okay, and now let's compare some components failure rates. Different components are produced with different technologies, and for example, the microcontrollers and mechanical devices, there is a big difference. The most safe or dependable systems are the military units. For example, the failure rate in millions of operations or for military microcontrollers, microprocessors is 0.02 failures in 1 million operation or, which is actually low. If you take a look to a cheap automobile microcontroller, microprocessor, it is almost 10 times higher. So you have 0.1 failures in millions operations hours. So, but no car is going to be running for millions of hours, but you have millions of cars, and then you have every 10 hours a failure in these millions of cars which you have distributed. Now we are coming to electrical motors, mechanical parts, and you can see there is a very big jumps. Electronic parts have a very low failure rate. Mechanical parts have much higher error rate. We are talking about here factor 100 higher, or an oil pump, much complex, 37 errors in millions operating hours, and the wiring, they break, then you have an extreme error rate of 700 errors of failures in 1 million operation hour. So if you have 1 million cars, then 700 cars failures per hour. That's really a lot. Therefore, in space missions, we try to avoid mechanical parts. Electronic will be working very reliable for a long time, but all mechanical parts are very dangerous, especially in space where there is no chance to repair. Well, here on Earth, if an electric motor of your car fails, then you bring it to the shop, it will repair and you can continue driving. But in space, if the motor fails, then it's done. So you have to have at least 2 motors. If one fails, you take the next one. And if you take a look to this, then the probability of failure is 100 times higher. Only the electronic will live 100 times longer than the mechanical parts. Okay, now, just a second. And now let's consider a system which consists of many components, a complex system. Up to now, it was only one component and we have the probability of failure of one component. Maybe we can make these measurements with the integrated system, but let's talk about a system which consists of many components. Okay, we have a chain and all of components have to be working in order to keep the system working. If one component fails, then we assume a system failure, the whole system is going to fail. Okay, then let's talk about the reliability of the system. Okay, and this is what we saw before. The reliability for this time period is a to the power of minus error rate for the component key multiplied by the time period. The longer the time, so lower the probability the system will survive. Okay, and now let's assume we have a chain of many components. And then the probability that the whole chain will be working is the probability that each then will be working multiplied by the probability of the next and the next and the next. So it's the multiplication of the reliability of the first one multiplied by the reliability of the second and the third and so on. And you remember this reliability is a number from 0 to 1. So multiplying numbers which are lower than 1, you are getting smaller and smaller numbers. So the longer the chain, also lower will be the probability the chain will survive. So for the whole system, for the whole chain, then we have the multiplication of all components of the reliability of all components. This times this times this times this. Okay, and as you remember, the reliability of this then will be e to the power of t multiplied by the reliability or error rate of each of these. So, and the total error rate here will be the sum of all error rates of all components. So at the end you have a to the power of t multiplied by the total error rate, which is the sum of error rate of all individual components. So the longer the chain, the lower the probability it will survive. But now for an example, let's assume all are the same type. For example, we are talking about transistors. All transistors are the same, so the probability error rate, this will be the same for all components. Then we have this situation. The probability will be the error rate multiplied by the number of elements. Let's say we have 100 elements. Well, if we are talking about transistors, 100 is almost nothing. Okay? With transistors, we are talking about millions or hundreds of millions or billions of transistors. So if each of them has a probability of 0.9999, a reliability of 0.999, if we have a chain of 100 of them, that it will be this number to the power of 100, then it will be 0.90. See? So the probability is dropping very drastically with the number of components. So if we have very few components, we can keep a higher reliability, and with the number of components are growing very fast, then the reliability of the chain will drop. Okay, and let's assume what if we want to improve the reliability. I showed this in the previous video, but I'm going to show again. As you see, it's dropping very fast, and to improve the reliability, here we have to reduce this number. So we have to reduce the number of components, the error rate of each component, of the period of time which we want to operate the system. Let's assume this graph is n number of components multiplied by the time. And then we can see as the time our number of components is growing, this is going to drop. Okay, what can we do? The time which we are going to operate the system, okay, we reduce this, but let's assume this is a constant. Then the only thing we can reduce is the number of components or the probability of failure of each of these components. To reduce the probability of failure of each component could be difficult, okay? The easier thing is to reduce the number of elements in this chain in order to improve the reliability of the system. And now, a little bit more complex. We don't have only a chain, we have parallel systems. For example, like this, we have redundancy systems. Let's assume this complex system. To be able to operable, just a second, these are redundant. We can use number one. If number one fails, then we can use number two. For example, these two chains. If one fails, then we can keep this hanging with the other chain. And then we have a chain. This is one part. And this has to be working, and this has to be working. Here we have redundancy again. We can have the component number 5 or 3 and 4 working at the same time. So if we want to go from here to here, there are different ways we can take. For example, 1, 3, and 4. So 1, 3, and 4. Or 2, 3, and 4. 2, 3, and 4. Or 1 and 5. 1 and 5. Or 2 and 5. 2 and 5. Okay, these are the different combinations we can have in order to keep the system working. And now let's talk about probability. Do you remember? No, not remember. Let's talk about the inverse of reliability. The probability of failure is 1 minus the reliability. Let's say Q is the probability the system will fail. And reliability is the probability the system will survive. Then we remember what is reliability is e to the power of minus error rate, multiplied by the time period. And Q is 1 minus this. 1 minus this. Okay, then if we have parallel systems, the probability of failure of the whole system is the probability one is going to fail and the other is going to fail too. So the multiplication of both probability that both fail at the same time, other in the same period of time. So if we have a parallel system, Q1 and Q2, then the probability of failure will be the multiplication of 1 plus the multiplication of probability of failure of the second. And you remember, the probability is a number from 0 to 1. If you are multiplying numbers which are lower than 1, then the longer you multiply, also smaller is the number. So the more systems you have parallel working, the lower is the probability that all are going to fail at the same time. Okay, that is the probability of failure. Now we want to talk about the probability of working, the reliability. And this is, of course, 1 minus the probability of failure. And this is the reliability of parallel systems. And this is 1 minus the multiplication of 1 minus the reliability of each component, which is this. This is this, as said before. Okay. Now let's take an example. Let's assume we have a very unreliable system. For a period of time, let's say for 1 year, the probability it will be working is 0.95, working continuously for 1 year. And then the probability that it will fail is 1 minus this. So the probability of failure is 0.5. And now let's say we have 4 parallel systems. Then the probability that all of them are going to fail is 1 minus this to the power of 4. And this is 0.999993. So the probability that all 4 parallel working systems fail in this period of time, let's say 1 year, is very low. And this is, if we take a look, the probability is 1 to 160,000. And this is very good in the given period of time. So this is if we are operating parallel chains, parallel systems. And now let's consider this again. What is the probability, the reliability of this for a period of time? Let's say the probability it will be working for, let's say, 1 year. And then we make some computations and we say, okay, the probability, the reliability of this for 1 year is 0.9. The probability of this is 0.9. For this is 0.99, 0.99 again, and 0.85. Okay, any numbers. And using what we saw before, let's compute the probability for the reliability of everything. First, the reliability of this. They are connected in parallel, then Q for 1 multiplied by Q from 2. And this is the probability of failure for this chain. But we don't want the probability of failure, we want the probability of success. Then we subtract 1 minus the probability of failure of both together. And this is the reliability of this part, 1 and 2. And we do something similar like this. The probability this is going to fail is 1 minus 8.5, this for R5. And the probability this is going to fail is the reliability from this multiplied with the reliability from this, and then minus 1. And this is the probability this is going to fail. And then we want the reliability of both. First we have the probability of failure here, and we have the probability of failure here. Then the probability of failure of this part is this multiplied by this. Q from this part multiplied by Q from this other part. Okay, and then we want the probability that it will work, the reliability. Then we subtract it from 1. And then we have the reliability for this and the reliability for this. And the reliability for both together is this multiplied by this reliability. Okay, this multiplied by this is what we have. And if you make all these operations, you will see the reliability of this chain is 0.987. Okay, then let's summarize the values which we have seen. The rate of occurrence of failure, the probability of failure, the probability of failure-free survival of the mission, the availability as probability, the reliability as probability, what is safety, the mean time to failures, time between failures, and restart and recovery time. Okay, this is what we have seen up to now. And now for this video, thank you very much and see you in the next video.